Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar, Test and Repair of SoCs for Functional Safety Applications, brought to you by Tech Online, Synopsys, and broadcast by UBM. I'm Chris Keach, and I'll be your moderator today. We have just a few brief announcements before we begin. First, the slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on the green folder icon located at the bottom of your screen. You can also participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A text area located to the right of the presentation window, and then click the Submit button. At this time, we recommend that you disable your computer's pop-up blockers. This will allow the slides to advance automatically throughout the event. And at the end of the webinar, we will ask you to complete our feedback form. Your feedback will provide us with valuable information on how we can improve future events. You can also launch the survey at any time by clicking on the red survey button at the bottom of your console. And if you're experiencing any technical problems, please type your issue into the Q&A text area, and we will be glad to offer one-on-one assistance. And now, on to the presentation. Test and repair of SoCs for functional safety applications. Discussing today's topic is Yervant Zorian. Dr. Zorian is a Chief Architect and Fellow at Synopsys. Formerly, he was a distinguished member of technical staff, AT&T Bell Laboratories, Vice President and Chief Scientist of Virage Logic, and Chief Technologist at Logic Vision. He is currently the President of the IEEE Test Technology Technical Council, or TTTC, the founder and chair of the IEEE 1500 Standardization Working Group, the Editor-in-Chief Emeritus of the IEEE Design and Test of Computers, and an adjunct professor at the University of British Columbia. He served on the Board of Governors of Computer Society and CETA, was the Vice President of the IEEE Computer Society, and the General Chair of the 50th Design Automation Conference, or DAC, and several other symposia and workshops. He received his MS degree in computer engineering from the University of Southern California, a PhD in electrical engineering from McGill University, and an MBA from the Wharton School of Business, University of Pennsylvania. It's with great pleasure that I now turn it over to Yervant to begin today's presentation. Yervant?
Thank you, Chris. Today's topic is on test and repair of a particular category of SoCs these are the SoCs that are meant for functional safety-oriented applications, and automotive ICs are definitely among those. Today the intent is to cover a little bit about the safety basics, functional safety, what do we mean by that, and then moving on to the needs for the automotive industry, and particularly concentrating on certain types of blocks in our SoCs, such as the memories, the analog mixed signal blocks, and so on. Towards the end, coming back to the functional safety aspect and discussing a little bit the standard 26262 and how the SoC level functional safety can be controlled by that. So the functional safety basics are this. Functional safety itself is not a new thing. It has been there for a long time. Functional safety critical requirements have been established long ago in different types of applications, in aerospace, in military, in medical, and so on, including transportation. The news here is that the complexity of the chips have grown. The complexity of the SoCs that are feeding this market is growing very fast. And therefore, managing the safety for those is a key element that needs to be met. Safety means risk mitigation, means operating errors, hardware failures, environmental changes that would create failures in the chips that will propagate to the system, and they need to be mitigated somehow. Now, thinking of that, safety or functional safety is a hierarchical approach. For the system to be functionally safe, we need the subsystems to do that. We need the components, that is the chips, to do that. We need the different pieces of the chips, that is the IPs, the building blocks, to do the same. And we, Synopsys, being a key supplier of those IP blocks, of the tools, the automation that are needed for these chips, we need to ensure safety from early stage, building up into the system level functional safety. So there are multiple standards that have been met for this. You see a list here for airborne-oriented applications, medical, machinery, as well as the vehicles, that is the automotive industry. The last one, 26262, is the newest one that is being used today for the automotive industry. There, we have to meet certain rating levels. ASIL, Automotive Safety Integrity Level, is this certain rating. And it can be A level, B level, C level, D level, as you see, because it depends on the criticality of what we need to do. And that criticality is a composite factor. It's a composite factor made of the severity, the controllability, as well as the exposure of the failures that are happening. And the most stringent level of this is the ASIL D. As you see on the right-hand side, ASIL D is the most stringent level where the most critical applications in the automotive industry will meet that, the autonomous cars and otherwise. So if you meet ASIL D, you would have met the C and the B and A. So for us as building block providers, meeting ASIL D is a very good goal. With that, we would cover the entire space of the automotive industry. So let's talk about the automotive industry a little bit here and see what are the trends that are there. You all know that it's one of the fastest growing sectors in the industry, and we are seeing a very large growth in the business of the automotive industry, far more than all the others. And the key thing there is that there are newer types of applications, newer types of IPs that are coming into the picture. For instance, the Advanced Driver Assistance Systems, that is ADAS, is one of those domains. Similarly, the infotainment chips are one of those domains. These are complex chips that are necessitating a very wide range of IPs to be incorporated, wide range in their variety, and also in the amount, in the number of IPs that are needed for those chips. So as we build those chips with huge number of IPs, we need to be able to take care of their health properly. Their health being their test, their repair, their safety, their security as well. Here you see an example of a chip from Renesas, which is surrounded by numerous interface IP blocks. So you see the variety, the heterogeneity of those, and the fact that we need to be able to take care of them, not only as test and repair, but also as safety, as they interface with their surrounding environment. Here is another such example from Toshiba, the Visconti series, again interfacing with numerous cameras, handling lots of video decoding and processing, as well as multiple other interface factors that are necessary. Now, as you build those chips, you build them in a way to create the functionality, but this way is hierarchical. So the hierarchy of the chip is made of IPs sitting in cores, sitting in CPU, sitting in sub-chips, in chips, and so on. And as we'll talk about the testability as well as the safety, we need to build it hierarchically as we move forward in order to ensure that the entirety, that is end-to-end system, is safe in that sense. So Synopsys, as I said before, in multiple ways is contributing to this automotive total solution by providing IPs and tools. And there we maintain the health of those chips, not only the functionality, that is the quality of the chip, the reliability, its robustness, its safety. Among those, there's a key item, which is the test-related IPs. The test-related IPs are meant to take care of the memories, to take care of the logic, to take care of the mixed signal blocks. And for that, we don't only take care of the manufacturing test, but rather the test is something that starts early on in the design stage and ends up being utilized in the field. So in the design stage, we start by building automated capabilities to incorporate the DFT and the built-in self-test engines from the smallest building blocks and moving forward while taking care of the area, the performance, the power. And we'll talk a little bit about that design space. Moving on to the early silicon, the early bring-up stage, and how can we debug our chips and make sure that they're functioning properly, going to the volume production, especially high volumes when necessary, and then to the field. And this is specific to the functional safety-oriented applications where the test will not stop in the factory, but it will continue upon power-up. It will continue for periodic tests during the mission mode operation, and also doing corrections during mission mode operation. And the reason we do it all in the field as well, because we do have failures that happen in the field. There are permanent type of failures that need this periodic test, and there are transient type of failures, such as soft errors, that will need self-correction and so on. So for these two types of failures, field-oriented testing is a necessity. Now, having understood a little bit the, the background of it, let's focus into then an SoC. An SoC typically has large number of memories. In this automotive industry itself, we have numerous memories sitting in the chip, often thousands. And for that, we need to take care of the memory from its early stage in the same kind of situations that I mentioned a bit earlier, in the design stage, in the manufacturing stage, as well as in the field later on. And we'll touch each one of those a little bit to understand what one would do with the memory subsystem in these automotive chips. This is my SoC. I see in it numerous types of memories, whether they are SRAMs, ROM, register files, caches, embedded flash, be content addressable memories, and so on, all of which are sitting to do their function in different blocks or subchips. But while doing their functionality, we need to take care of their test. So doing bits with memories is something that has been done for a long time. We have done it for the past 25 to 30 years. Every single memory gets self-tested, which is nice. They get repaired as well for the last 10 or so years, which is also very good for yield purposes. Now, in addition to that layer, we need to have also the safety measure being considered for them. So while we'll continue to build that, we'll be able to add that safety too. Now, safety requires, like the rest, requires communication. So these building blocks, whether they are wrapper IPs for every memory, whether they are processors that contain test and repair algorithms, or they are servers that sit on the top level to manage the entire chip, we need to be able to communicate between them. And gladly, we do have IEEE standards that have been developed to help us with this communication. We do have IEEE 1500, which is an IP level standard that does a very good job for this purpose. We do have 1687, another IEEE standard, which is meant for hierarchical level testing, that is switching between different levels of hierarchy, up to the top level where you see this TAP, that's the IEEE JTAG 1149.1, which is again meant for this purpose, to access the infrastructure and handshake with it. Now, what we build here is not only at the design stage. We also need to provide the post-silicon capabilities, and what Synopsys provides as star memory system does that. So on one hand, it's an IP that gets incorporated in the chip, inserted, verified, and then post-silicon being analyzed for silicon debugging and volume testing purposes. Now, all of that is meant for any memory. And today there are many SoCs with different sources of memories that use this star memory system. But there is one additional feature there that needs to be mentioned. That is, if those memories are being used with, if this star memory system is being used with the Synopsys memories, we have extra advantages. That is, leveraging what can be part of the memory itself, where certain SMS, star memory system oriented hardware, can be incorporated into the hard macro of the memory. With that, we can have several nice advantages. Here you see three types of memories. The one on the left-hand side is a pure memory without any testability, any repairability incorporated in it, whereas the ones in the middle and right-hand side are the IT and ST modes of our SRAMs that have absorbed in them certain functionalities of the star memory system. And those functionalities will allow us to absorb the routing congestion, to absorb some of the timing implications, to absorb some of the power, thus giving us a good level of advantages in terms of frequency, as you see, in terms of minimizing the overall area, not only the memory and the SMS area, but rather the entire area of the chip is minimized, the entire power of the chip is being reduced, and the coverage optimized. So there is this extra very nice advantage of using the test and repair system with the memories from Synopsys, especially both of which being meant for the automotive industry. Now, similarly, one can tilt or one can optimize solutions for different other blocks. Like you do it for memories, you can do it also for processors. Certain places where the data path is critical in terms of timing, and then you can put your BIST muxes in order to optimize the speed, that is the normal functional speed of the processor, and thus have your self-test algorithms, self-test coverage, and repair coverage meant with smallest impact in terms of performance. Here you see, for instance, an example of an ARM Cortex processor where the multiplexers are already built into the processor in advance, and the processors do contain the connections of the multiplexers to a unified bus, and that unified bus brings together the SMS meant for this purpose. So the SMS, that is the star memory system MMB, in the blue boxes here, are specialized SMSs meant for multi-memory bus connections, and they take care of the cases where the BISMUXes and the buses are already incorporated in the processor, and they provide the necessary test and repair infrastructure for this. Now, all of this is good during the design stage, during the manufacturing stage. Now let's come to the utilization aspect. Now we'll talk a little bit about the utilization in the production space, but more of it in the field itself, during the power on mode and during the mission mode, as we will do our best to provide the necessary aspects of this in the field as well. So in the production mode, what we do is we do the analysis in advance to understand what kind of failures could happen in manufacturing, in production, such as in the FinFET cases. We have analyzed the FinFET specific defects. I'll come to that in a second, to understand what kind of implications could be there. And accordingly built our BIST engines, BIST algorithms, to have minimum DPPM, that is defect per million, in order to ensure that we have very high quality, especially in these types of automotive applications. Same, while we're doing that, we need to take care of the yield. We need to take care of the diagnostics as well to understand what kind of failures are happening, to locate them, to classify them, and so on. So to understand the defectivity, this analysis is important for various types of failures. And we have extended that recently to contain all the FinFET-oriented failures as well. And we found out that there are several new types of failures that are happening in the FinFET domain that we did not see in the past. Therefore, we had to increase our fault models. We had to increase the coverage of our algorithms to contain the specific failures such as these gate opens, the fin stuck-ons, the fin opens, which have manifestations that are not similar to the planar technology, that are newer in terms of types. In fact, they are newer in the sense that they are more dynamic in nature, given the fact that the transistors are three-dimensional. The fins can be, some of which can be broken or not, some of which can be shorted or not, in a resistive way. That gives us the necessity to have dynamic nature in our tests. Okay? So while the static nature is still there, as in the planar technology, we need to have the dynamic faults as well. In the 16 and the 14 FinFET, we saw the risk of lesser risk of process variation. However, now as we're moving to 7, we see that coming back again. Therefore, the test under different corners, under different conditions is necessary. And also, as we are shrinking the dimensions, moving to 7, we are seeing the fact that we need to take care of not a single failure, but rather multiple failures per transistor being considered in those. Now today, gladly, the star memory system being used in automotive applications and otherwise does have the FinFET coverage, and the FinFET algorithms are part of the solution that we provide to our users in this domain. So today that is given by default for the multiple manufacturers of FinFET technology. So as you know, FinFET technology is being provided by several manufacturers these days, and gladly all of those have utilized SMS with our memories in order to prove the memories, their characterization, and their provider. Now, what we see here is that the test is not sufficient. The test needs to be augmented by debug and diagnostic capabilities. That's why what you put inside the chip in terms of IP is only part of the solution. The second part of the solution comes with the software, with the automation that will sit outside the chip to handshake with the chip in terms of debug and diagnosis. And there, these debug and diagnostic capabilities will be utilized when the first silicon comes back, and we need to ensure that we do have the necessary eyes inside the chip to look into the problems. And that is in multiple levels. That is zooming from finding which memory has failed, to which logic address was the failure at, to which physical address, which rows and columns do identify that failing point, the XY coordinates of the failing bit, to the defect classification of those, what kind of fault have happened, and localization. So there are numerous things that are needed in order to zoom into the problem point. And with these advanced technologies, and especially these days where the automotive industry has moved and is moving fast into those advanced nodes, we need to be able to do all of that to ensure the health of the chip from day one as we're analyzing the first silicon that comes back to us. Also, as we saw earlier, that there are lots of interfaces with our SoCs that are there, some of which high-speed interfaces that deal with memories, others dealing with video communication, with audio, and so on. So with the memories, as you have DRAMs talking to your SoC, often with DDR or high-bandwidth memories or otherwise, wide IOs, we need to be able to test and debug those memories that are sitting outside. And when the SoC is talking to those memories, it's very hard to come in the middle with this high-speed bus and interfere with that bus in order to ensure that both sides of the communication are doing their job well. Instead, building an engine, an SMS engine, not to test the memories, the embedded memories in the SoC, but rather to test the external memories sitting outside the SoC, such as those green ones sitting above the SoC, is very important. So what we do with this SMS blue box sitting in the SoC, we provide high speed, that is at speed communication for the test and the diagnosis to run through that connection and to be able to test the memories and to test the interconnect between the memory and the SoC itself, and to tell us not only which one is failing, but where that failure is in order to be able to replace it. So we know which memory and which line on the bus connecting to in case it comes from the bus. Of course, this has to go hand in hand with the protocol of interface, whether we are using different types of DDRs, whether we're using high bandwidth memories, we need to be able to handshake with it, and the SMS would sit behind it in order to leverage the speed of that interconnection. Okay? So you see the orange PHY sitting in the SoC, and you see the controller in blue sitting behind it, and the SMS sitting in parallel to the controller and communicating via the PHY to the interconnect and the memory to provide us necessary. So again, this will help us to debug and help us reduce the risk upon manufacturing. Now, most of these capabilities that we talked about are used also in the field, not only upon manufacturing, but once they become part of the system, they will be utilized later on as well. Why? As we said before, there are different types of failures, permanent failures, that will happen during the life cycle of the system. And power-on self-test is a requirement these days. It's called POST. It's a requirement of ISO 26262 to ensure that the chip can test itself when it's powered up. Now, the star memory system, while we invested in the IP to test the chip upon manufacturing, that same investment can be utilized in the field as well, of course, with slightly different conditions. Here, the repair has to be done much faster because when you power on, you have very limited time to bring the system to its normal situation. Therefore, you need to have parallel repairing, and we have a nice advanced repair capability that we built into this system. The self-test itself needs to be done again in a fast way. Therefore, it has to be concurrent and parallel, given the requirements of time that are needed. Also, the requirements of power need to be taken into consideration while doing that. And here, interfacing with this infrastructure need to be done from inside the chip. That is, the external sources, such as the tester, are not provided anymore when you are in system, when you are in the power on mode. Therefore, what we need to do is we need to have the initialization processor that is sitting in the chip that is starting the whole test and repair mode upon power up will take control of the server and will be able to supply the necessary signals to run it in an autonomous way, in a previously prepared, scheduled way, every time the power on happens in the chip. Now, we also have the requirement not to stop upon power on. Power on is important every time you power the automobile. Here we need to do also mission mode testing. For mission mode testing, there are two things. For permanent faults, we do have this periodic test where SMS can be also used for that purpose, but it has to be partitioned properly. So the blocks of the chip, those hierarchical blocks that we have seen, have to be functionally partitioned, and which pieces would run their mission mode, whereas which other pieces would run their test mode. And those test modes are very, very short because during mission mode, the time doesn't allow us to have large number of cycles to run the built-in self-test, and therefore we need to schedule that also in advance properly, and you have sub-chip isolation for where the test is happening and where concurrently the mission is running with the test time adjustments. In addition, we need to have the possibility of aborting the test when necessary. As the conditions do change around that chip, we need to stop the test and bring back the normal mode of operation. Therefore, there are very nice capabilities that are reprogrammable, that are sitting in those engines, that those engines become very useful in the field for periodic self-testing. So the investment that we put in manufacturing, the investment that we utilize in power on self-test, now we are using it also in mission mode, but in different schedules, in different time windows, and in different power constraint windows, in order to meet the requirements of these three different situations. In addition, now we do have these transient faults, and we need to protect against. And this is not new. We have done transient fault protection for a long time. Soft errors are there. They are still there. Their impact is changing from time to time. And today we're seeing that the change is that the single bit impact that they used to create has changed to multi-bit upsets, where in the past the multi-bit upsets were a very small probability of what happens with soft errors. Today, almost half of what happens as impact of soft errors is in multi-bit upsets. Therefore, the correction that we have need to be intelligent enough to take care of multiple failures at the same time, that is multiple bits failing at the same time. So the correction mechanisms need to have different correction codes in them, and therefore need to have higher granularity of repair. These self-correcting engines are very important, but not to be used on every memory in the chip. Typically, it's based on the functionalities of different corners of the chip, the criticality of those functions, and accordingly, the investment in ECC happens. So the star ECC that we have developed has this flexibility in terms of which granularity you need to put and which level of correction you need to do. The multi-bit correction has its levels. Is 2-bit correction, 3-bit, or 4-bit is a outcome of what the user specifies in advance. Plus, it has numerous additional capabilities, such as here you see the pipelining capabilities, the programmability capabilities, and so on, that allows us to have minimum performance impact versus and power impact versus area. So trade-offs to be analyzed and chosen accordingly. Again, a key element of testing automotive chips when they are in mission mode. We talked a bit about memories. Now we'll go towards other types of blocks, such as the analog mixed signal blocks that are in the chips. Those blocks, as we have seen, are increasing again in numbers. When we had 2 of them, as you see here in this picture, it was easy to access them, test them from outside, exercise them from the primary IOs. However, once we have many of them, it is very difficult to do that. And in today's automotive chips, as we saw from the 2 examples I showed earlier, there are numerous such IP blocks that are there. And therefore, we need to be able to test them properly and in parallel. If you see this SoC, for instance, you have various orange boxes there, interface IPs, analog mixed signal, maybe PLLs, ADCs, sensors, small sensors that, again, need to be handshake. Therefore, we need to build the access mechanism in order to talk to them, again, in those different modes. This access mechanism will be utilized during manufacturing test, will be utilized in power on, and in mission mode as well. Here also you see digital blocks. Again, in a hierarchical nature of SoC, the digital blocks will be also deep embedded somewhere in the cores, and we need to reach them again in an access mechanism like this. The star hierarchical system is something that we have developed. It's a nice solution that is being used for such hierarchical situations where you have different blocks in different hierarchies and you need to access them nicely. You would use the star hierarchical system to arrive there and to activate the test, to transport the patterns as necessary for them. So the way it goes is we start with a certain block, let's say this USB IP, by wrapping it with this blue wrapper around it, and having its patterns dedicated in advance, knowing what kind of tests are needed for this block. And then we take this and incorporate it to this middle subchip level, where the USB with few other IPs are in this subchip, and they have this purple infrastructure that allows us to access, allows us to control and observe, but also to transport the patterns now that are composite patterns for all these three IPs. Same thing can happen if I go right. I go to the next one, which is an automotive SoC that has multiple blocks like this. And again, the subserver, which was controlling the subchip, now would be connected to the server that is controlling the entire SoC from a test and repair and safety infrastructure. And will allow us to take those signals from the IP level, bring it to the subchip level, to the chip level, and report up as necessary. For manufacturing tests, the reporting is done typically through the tab controller. For non-manufacturing tests in the field, whether it's power on or mission, the reporting is done through the internal processing engines inside the SoC. And for all of this to happen, we need extra level of sensors to be built inside the chip. Again, the star hierarchical system that we have created for such purposes do come with numerous types of engines that help us sense and measure the different signals. Whether it's timing oriented, that is performance, whether it's process oriented, it will give us the possibility to sense and to transfer that information as we move forward. Now, all of this would happen in a certain way where we can exercise whichever blocks we want to. Now, that exercising is different from situation to the other. When I am in the debugging mode, early stage, I would like to talk to one block at a time. Therefore, my SHS infrastructure should allow me to talk to one IP at a time, whether it's a mixed signal block, a PHY, a logic block, a memory as well. So I need to talk to one at a time, do the analysis, do the debugging, and so on. When I'm in manufacturing test, I would like to run many things in parallel to minimize the test time, as long as the power of the chip allows me to do that. Again, this SHS infrastructure that we built need to be fully programmable to allow me to run now the multiplicity, maximum concurrency in order to minimize the test time, therefore minimize my production cost. When I go to power on self-test, there the situation is different. There also I need to have fast self-testing, but my power limitations could be different when I'm in the system versus in the chip by itself. And of course I need to take care of both types of power dissipation, when it's active, when an IP is active, an IP is passive, and to calculate that entirety. But again, in the power on self-test, I am dealing with test only, different than the mission mode. In the mission mode, the difference is that I'm running functional mode and test mode simultaneously in different blocks. There, the power calculations, there, the test time allowed are different. Therefore, the scheduling is very different in building up my mission mode self-test activity for the permanent faults that would happen during the life cycle due to aging or other factors. And there, again, the scheduling will become critical. So scheduling, test time, power, as well as the functionality can be of different sorts. I could do these together, I could do these together, or I can do it in a different way. So the same SoC can have multiple test schedules depending on the needs. In production mode, the need is the shortest test time for the entire SoC. In the power on self-test mode is the test and the repair with power on in the system. Then if I move on, in the mission mode, I have different composition, and the time is the most critical one, which I need to meet. Here is an example of a chip where I can see where the test is being run in parallel and where it is not. And it's a simplistic example. In this case, you see there are two PCIEs. If I run one at a time, it will take certain amount of time in order to do the test. If I run the two PCIEs together here, my time doing them in parallel is shorter than doing them sequentially, that is back to back. And there's about 20% gain by doing them in parallel versus back to back. If I bring in my DDR4 with these two PCIEs and then run all three of them in parallel, I gain even more time. I have about 25% gain in test time by having these three IPs, it's a simple case, running them together. If I have 10 of those, my gain will be drastically better. And depending on the test pattern that I'm running. Initialization pattern is different, internal looping, external looping, built-in self-test. There are different modes, different patterns for each one of the IPs. Gladly, with our Synopsys IPs, we do provide these different modes already automated and ready for SHS utilization. In this latest case, for instance, you see about 83% reduction in test time because of the concurrency that SHS is providing us. And in automotive applications, concurrency being very important, we need to be able to take care of this nicely. Now, if I summarize the SHS part of it, I would see that I'm doing reduced test time for manufacturing test, for mission mode test, and power on. I'm doing very high fault coverage because the IP test itself is getting integrated into the total test. It's not somebody else writing the test beyond the IP. We established long ago that the IP test should come from the IP provider because the IP provider knows how to best test that IP, whether it's memory or mixed signal or any other IP. And cost reduction. With the parallelism that we can create, with the concurrency that we can create, cost reduction is definitely a very good outcome that one can obtain. So coming back to what we have covered so far, we have covered the needs for the test, the different modes of running the test and repair for these safety applications. Now let's step back for a second and see how well we are meeting the safety application itself. Now, when we build a chip, we build it based on requirements. Typically, there's this V curve that comes out from a requirement that comes, the vehicle level requirements that comes from the OEM, from the car company, goes to a system design at that level, then goes to a tier one, which is concentrating on the electronics of this subsystem, if you want, and then going on to a semiconductor company, this chip company, which will do the design and the manufacturing of the chip and will provide it to us. And from there, we'll test it, we'll verify it, and we'll validate the entire car back to that level. In our case, when we speak about the functional safety, it starts from the top level of the V to the other top level, going throughout that entirety. And in fact, this 26262 standard that we talked about, the ISO standard, is exactly meant for that, is exactly meant to start from the top level, go on to ensure that every single component of the car meets that standard, the chips do meet that standard, and for us, the IP inside that chip meets that standard. And that is how to detect and how to react. The game is there that there are certain functionalities that are meant to be run for that safety purpose. That is when the risk happens in the field, when a failure happens, whether it's hardware failure or an environmental damage due to soft error, you have your ECC there, you have your self-repair there, and you verify all of that with injecting faults, with diagnosing them, and ensuring that they are all met. Gladly, with the SMS and the SHS solutions that I've shown you, we have gone through this extensive exercise we have gone through the certification, and they are both of them have met the ASIL level D, which is the most stringent level of ASIL that we have. So that is today we have this ASIL level certification already met for the two of them, and for that we had to go through external certification, where fault injection done by the external parties to ensure that the FMEDA, which is the diagnostic, the failure mode, and diagnostic analysis, is done for the particular IPs such as SMS, SHS, and ensuring that every injected fault will propagate, will be detected, and will be executed properly, and the mitigation will happen accordingly. There's a very narrow time window for that to happen, for that to be completed, in order to meet the ASIL D level requirements. Of course, the others are slightly lesser stringent in that sense. So today, we have developed an ISO 26262 package for SMS and SHS, which is being used by the automotive industry. We have also trained a safety manager. We have prepared the engines, the manuals that go with it, and the processes to create all of that, certified by SGS TUV. And these packages are helping us now meet the complex chips in the automotive industry. So as a result, today, those functions in the design, in manufacturing, and in the field do have corresponding features inside the SMS and the SHS to be run in manufacturing during silicon debug production, to be run also as power on self-test, to be run as periodic tests during the mission mode, this parallelism that we talked about of mission mode and self-testing in the field, as well as the correction, that is multi-bit offset correction by our star ECC that is meant for this purpose. To summarize, what we have covered together today is the fact that functional safety needs to be met properly. Our test solutions, not only our functional IPs, not only our functional automation tools, but the test tools and the test IPs, such as SMS, SHS, in addition to Tetramax ATPG, have gone through this certification process and have met the ASIL level that corresponds to them. And this certification has met the needs of the industry today. So as we move to more and more difficult chips in the autonomous cars or otherwise, we'll be able to meet the expectations and provide the necessary. So we have, therefore, the needs for automotive ICs in terms of design, test, the reliability in the field, and the safety, which is reporting and mitigating the problems, all of which need to be prepared for, all of which need to be prepared with the IPs that we produce. So an IP needs to be able to test itself, to maintain its reliability, to maintain its health, and the safety. In fact, if I go one step more, security becomes also a critical element there that is added to those same IPs as well. So the automotive test today has this high-level solution for test and repair. It's an important capability. It meets the area, performance, and power of the chip with almost no penalty. It provides the coverage at the most advanced nodes of FinFET, moving towards 7, and also meets the safety, that's the functional safety standards, which is ISO 26262, and the certification that we have obtained for. And with that, I'll complete my talk, and we'll pass it on back to Chris.
All right, thank you, Yervant. Now, before we begin with today's Q&A, please fill out the feedback form that's opened up on your computer. If you do not see if your pop-up blockers have prevented your computer from launching the feedback form, you can click on the red survey icon at the bottom of your screen. To complete the form, please press the Submit Answer button at the bottom of the page. Thank you in advance for filling out the feedback form. Your participation in this survey allows us to better serve you. We're now going to move on to the question and answer portion of the event. As a reminder, to participate in our Q&A, just type your question into the text box located to the right of the presentation window, or click on the Q&A icon at the bottom of your screen and enter your question, then click the Submit button. With that, we're going to go ahead and get started with our first question, and let's take a look at what that is. Looks like our first question for you, Yervant, is does the star BIST machine and the algorithms depend also on the specified operation frequency of the memory when the IP is generated?
Yes, it does. It does. So, but as you know, the memories have different performances and different needs for testability. So, in this case, we're talking about the automotive industry, where we have certain very high level of expectation, very low DPPM, almost zero DPPM that we like to. Therefore, we recommend having the strong algorithms to cover that. Now, if we were in other applications, gaming, let's say, where the quality requirements are lesser, then we do have other algorithms that we recommend for. I say recommend because, after all, it's the designer who builds in the algorithm into the engine. Our engines are programmable engines. You would put an algorithm by default there in advance during design, so the designer chooses and implements that. However, in the field, not in the field, that is in manufacturing, if the test engineer would like to change that algorithm, he can override the existing default algorithm, which is in the silicon, and can change that. And the speed would go with the speed of the memory. Typically, we recommend using the speed of the memory to run the test algorithm at that speed as well, to have at-speed coverage.
All right, thank you, Yervant. Our next question for you, how is repair realized?
The repair is typically realized with the memories. We do repair, of course. With other IPs, we have calibration, we have trimming, which I would also consider them under that repair umbrella. But let me specifically talk about the memories, since I use the term repair for memories in this presentation. Memories often would have a defective bit, depending on which technology you're using. The more advanced nodes, the more higher the probability of having failed bits. Now, repair uses the concept of redundancy, that is, having extra bits in the memory that are sitting there and waiting for utilization. It's like the extra tire you have in the back of your car. You have extra bits in the memory, and those bits can be configured, can be reconfigured, such that they would replace some defective bits in the memory. Now, having extra spare and having defective bits are possible, but with those, you need the intelligence. The intelligence is in these engines that we provide. So the engine, the star memory system, does the detection of the bad bit, has the diagnosis, finding where that bad bit is, and then the decision to replace it with a spare bit and reconfigure it softly inside the chip in order to replace the bad bit with the redundant bit, that is the extra bit. And that information now needs to be saved in the chip. Thus, we use an embedded non-volatile memory, such as an if-use, in order to save that information of which bit should be replaced by which. Okay? And the user would not see all of that. Upon manufacturing, this infrastructure will allow the defective bit to be detected, diagnosed, assigned or allocated to a good bit, and the if-use being prepared for it as well. And each time you power up your system, that reconfiguration happens by itself. Thus, that reconfiguration brings the defective memory to become a defect-free memory. Now, all of this is good as long as you have enough redundancy to replace bad bits. If you are in a bad corner, if the yield is bad for some reason, and your defective bits are more than your good bits to replace them, then you have difficulty. Of course, the chip will not be repairable and will be declared defective.
All right. Thank you, Yervant. Our next one for you. For a real-time SoC peripheral that cannot be shut down, is there a recommendation to implement periodic self-test in mission mode?
Yes, periodic self-test in mission mode for these kinds of applications, for safety-critical applications, is required. So in ISO 26262, we are required to provide the capability. And the SMS is built for that purpose. That is, it allows us to shut certain part, control, isolate it, and run the self-test of that part accordingly, with certain restrictions. So partitioning it is very important. Which part works with mission, which part works with test, and mission and test being concurrent to each other. That is the partitioning. Besides the partitioning, there is the duration of the test. So there too, how many seconds, or not seconds, of course, microseconds, would you allow for that test to happen? That is also factored in. And often, one memory is not tested in one shot. It's tested on multiple blocks. So sub-blocks of the memory are tested, then you go back to normal, then come back with another sub-block, then continue again, and so on. So it is a very incremental type of test that happens during mission mode.
All right, Yervan, our next one for you is, can you talk a little bit about how to repair analog and mixed signal IP?
Yes. So analog and mixed signal IP repair is not similar to what we do with memories, what I mentioned a bit earlier, which is redundant elements being added to the memory and switching. Instead, if you have different levels of good or bad in the analog mixed signal elements, in the high-speed IOs, the PHYs, and so on, there you can calibrate it to the window that you need it for. The calibration and also trimming are well-known capabilities that one uses for PHYs and mixed signal blocks. Now, what we are providing here is the ability to run that calibration even in the field. If you do it while manufacturing, storing that information in the fuse box and controlling through the eFuse during power on the calibration and the trimming handling of those IPs.
All right, and our next one for you, what industry standards is the STAR hierarchical system compatible with?
Yes. So the STAR hierarchical system is compatible in terms of its communication with a series of standards. From a DFT point of view, it meets three key standards. The three key standards are at the IP level. We typically have a 1500 port sitting in the IP to communicate with that IP and allows the IP level communication inside that IP and outside that IP to go through that. Now, in the past, when IEEE 1500 was created, the chips were in two-level hierarchy. That is, we had IPs and SoC. However, today, after 15 years of that, we do have multiple, as I showed, multiple levels of hierarchy. Therefore, the IP is sitting inside a larger core, inside a subchip, inside a chip. Therefore, the 1500 only and going to the top level JTAG 1149.1 is not sufficient. You need in-between levels as well. There, for the in-between levels, for the controllers that come hierarchically, we are using 1687. IEEE 1687 has this SIB, NIB, SIB, and NIB concept where you can block, open, and close widths of scan chains. We do that in order to continuously build the hierarchy and not being impacted by the huge number of IPs that we are seeing today. So to summarize the DFT side, at the IP level, we believe that 1500 is the best solution. Today, there are many IPs that come with that already. In between the different levels of hierarchy in the SoC, we use IEEE 1687. At the top level, we use 1149.1 as DFT. Now, in terms of patterns, we do also have different IEEE standards that we are utilizing to describe the patterns. CTL and style have been used by us for a long time. We continue using those for logic blocks. We continue using at the top level PDL and ICL, which came with 1687, and they're very good to describe the hierarchical level test of the different IPs. So you go there and you choose which IP you want to run, and you do have the PDL of that IP to execute. And ICL gives you the infrastructure to approach that. And of course, at the top level for manufacturing test, we generate as well WGL, Wiggle, and style to give us the possibility of running the test in a manufacturing test mode. As for the interactive mode, we do provide the software to have interactivity via JTAG. There also we're using the JTAG interface for interacting with the chip. So depending on the situation, therefore, whether you're at the IP level, at the hierarchical levels, or the top level, we use different DFT and pattern description languages to the best of their capabilities. Being involved in the test technology standards and test TC domain, we know how to use best those standards, and hopefully the industry utilizes that accordingly.
All right, Yervant, looks like we have time for maybe one or two more here. This one is the next one here. So, from analog and mixed signal IP, standpoint, what is the special requirement from functional safety standpoint different from other applications?
I would not think that there are different requirements for analog versus memory versus logic and so on. In fact, the functional safety requirements are at the chip level, because the chip is manufactured and has to meet the requirements of functional safety. What we do at the IP level, we do the preparation for that. So they are prepared for the functional safety. Of course, they are not manufactured yet as IP. When we supply those IPs, they are ready for the ISO 26262 at a certain ASIL level, but they are not manufactured yet. Therefore, they are not meeting that yet. Now, the entire chip need to meet either ASIL A, B, C, or D, depending on where the chip is being used in the car, what's the criticality of that application, and so on. So the chip itself would be either A, B, C, or D. The IP, whether it's mixed signal, memory, or logic, would need to meet to one of those. And our choice, when I talked about SMS and SHS, was to go with D. And the fact that we chose to go with D to meet all the requirements of the D level, because it's more stringent, is to ensure that this IP can be used in the most difficult chips in terms of situation, as well as the easier side of it. So by meeting the D level, you can do both.
All right, Yervant, I've got time for one more quick one here for you. So does the STAR memory system work with third-party memory compilers?
Absolutely. In fact, we do have a large number of users who use it with third-party memory compilers. We do have a nice handshake between the third-party memory and STAR memory system, by which we understand the particularities of the memory in terms of design, in terms of testability needs, and in terms of any redundancies or repair infrastructure that memory need to have. Most importantly, the physical infrastructure of the memory is also given in that model. By that, we would be able to know the XY coordinates of the defectivity. We'll be able to create true checkerboards for their tests and so on. So the answer in short is yes. We do have many cases where third-party memory compilers are being used today with SMS. I mean, older nodes up to 14, 16, and even 10 today.
All right, thank you, Yervant. That looks like all the time that we have for today, so my thanks to Yervant for a great presentation and Q&A session. And for more information related to today's webinar, please visit any of the resource links available in the green folder icon at the bottom of your screen. Within the next 24 hours, you'll receive a personalized follow-up email with details and a link to today's presentation on demand. And as a reminder to our audience, if we did not get to your question today, someone will get back to you via email. Thank you again for attending today's webinar, Test and Repair of SoCs for Functional Safety Applications, brought to you by Tech Online and Synopsys. This webinar is copyright 2016 by UBM. The presentation materials are owned by or copyrighted by Tech Online and Synopsys, and the individual speaker is solely responsible for his content and opinions. On behalf of our guests, Synopsys and Yervant Zorian, I'm Chris Keach. We'd like to thank you for joining us, and we hope you have a great day. Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar, Test and Repair of SoCs for Functional Safety Applications, brought to you by Tech Online, Synopsys, and broadcast by UBM. I'm Chris Keach, and I'll be your moderator today. We have just a few brief announcements before we begin. First, the slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on the green folder icon located at the bottom of your screen.